June 6, 1944. While the world watches thousands of Allied soldiers storm Normandy's beaches, there's a battle most documentaries never mention. A war fought with fuel, 1 million gallons every single day just to keep the invasion force moving forward. That's enough to fill an Olympic swimming pool every 24 hours, and someone has to deliver it. You might think the solution is obvious. Send tanker ships across the English Channel. Except that stretch of water has become one of the deadliest killing zones in World War II. German U-boats prowl like predators, and they're devastatingly efficient. A single torpedo sends thousands of gallons of fuel and dozens of sailors to the bottom. The Allies are losing tankers faster than they can build replacements. Every ship that goes down means less fuel reaching the front lines. Less fuel means stalled tanks, grounded aircraft, stranded troops. The mathematics are brutal. No fuel equals no victory. But even if tankers somehow make it across safely, unloading fuel at Normandy beaches becomes a logistical nightmare. The invasion will destroy most port facilities, and building new ones takes months the Allies simply don't have. German forces would use that time to reinforce, regroup, potentially push the invasion back into the sea. General Eisenhower understands that momentum is everything. Stop moving forward for even a week and the entire operation could collapse. So British and American military planners face an impossible question. How do you deliver 1 million gallons of fuel per day across 70 miles of hostile ocean, past enemy submarines, through unpredictable weather, to beaches with no proper ports, while under constant threat of German bombing raids? The conventional answer is simple: you can't. It's physically impossible. No technology exists in 1943 that can solve this problem. Tankers are too vulnerable. Aircraft can't carry enough volume. Fuel drums shipped on cargo vessels take too long to unload and distribute. That's when someone in a smoke-filled London planning room suggests something that sounds absolutely insane. What if we just build a pipeline under the ocean? Not a short pipe crossing a river, a pressurized petroleum pipeline stretching across the entire English Channel, sitting on the seabed, pumping aviation fuel and gasoline 24 hours a day, while war rages overhead. The room goes silent. Some engineers laugh outright, others assume it's a joke. One advisor calls it the most ridiculous proposal he's heard in 30 years of service. But desperation makes people consider radical ideas, and the Allies are desperate. This impossible pipeline needs to be designed, tested, manufactured, and installed in less than a year. And it all rests on the shoulders of one British engineer who's about to receive the most important phone call of his life. Arthur Hartley isn't a household name. He's not a decorated general or famous scientist, just a 41-year-old petroleum engineer working for the Anglo-Iranian Oil Company, spending his days solving mundane problems about moving fuel from refineries to storage tanks. Boring stuff, the kind of engineering work that never makes headlines. Then in early 1942, he receives a summons to a nondescript government building in London. The men waiting for him don't waste time with pleasantries. They lay out the problem in stark terms. Britain needs to pump fuel under the English Channel to support the inevitable invasion of Europe. It needs to work flawlessly under combat conditions, needs to be designed, built, and ready to deploy in roughly 90 days. And they need Arthur Hartley to figure out how. The meeting lasts less than an hour. Hartley leaves that building carrying the weight of the entire European invasion on his shoulders, and he can't tell a single soul about it. Not his wife, not his colleagues, nobody. This is classified at the highest possible level. Let's be clear about what they're asking him to do. No one has ever built a flexible pressurized pipeline that can survive being submerged in salt water for months or years. No one has ever laid a continuous pipe across 70 miles of open ocean water. Pressure alone could crush conventional pipes like aluminum cans. Ocean currents would bend and twist anything flexible until it snaps. Salt water would corrode metal faster than you could pump fuel through it. And even if Hartley somehow solves all those problems, There's still the issue of actually getting the pipeline to the ocean floor without it tangling, breaking, or sinking a ship in the process. Hartley starts with fundamentals. Standard rigid steel pipes are out. They'd snap the moment a strong current hits them. Concrete pipes are too heavy and too brittle. Copper pipes would corrode almost instantly in salt water. He needs something combining strength, flexibility, and corrosion resistance in ways that simply don't exist in 1942. So he does what good engineers do when existing technology fails them. He starts improvising. His first breakthrough comes from an unexpected place: telephone cables. Submarine telegraph cables have been crossing oceans since the 1860s, which means someone already figured out how to protect metal from saltwater corrosion. Hartley studies their design, multiple layers of protection with lead sheathing, providing a waterproof barrier. But telephone cables only carry electrical signals. Hartley needs to carry pressurized fuel at thousands of gallons per hour. The engineering challenge is exponentially more complex. He assembles a small team of metallurgists, welding specialists, and marine engineers, all sworn to secrecy. They work in isolated facilities, often not knowing what other teams are developing. Hartley visits each group, collects their findings, then synthesizes solutions in his head like pieces of an enormous puzzle. The pressure is crushing. Every week brings new demands from military planners. Every test reveals new problems, and the clock keeps ticking toward D-Day, whether Hartley is ready or not. Some nights he barely sleeps, running calculations in his head, wondering if he's chasing an impossible dream that will cost Allied lives when it inevitably fails. By spring 1942, Hartley's project earns its codename PLUTO, which stands for Pipeline Under the Ocean. The name is deliberately vague, designed to confuse German intelligence if they ever intercept communications about it. To anyone outside the inner circle, PLUTO could be anything: a new weapon, a radio system, a logistical code. That ambiguity is intentional, and Churchill himself has taken personal interest in the project, but a clever code name won't solve the fundamental engineering nightmare Hartley faces. He needs a pipe that can flex like a garden hose, but withstand pressure like a battleship hull. It needs to resist corrosion for at least 6 months of continuous saltwater exposure, be light enough to wind onto giant floating drums for transport, yet heavy enough to sink to the seabed and stay there during storms. And it needs to maintain structural integrity while pumping 80-octane aviation fuel at pressures that would make conventional pipes explode. These requirements contradict each other in almost every way. Hartley's team begins experimenting with lead alloys. Lead has several advantages: naturally resistant to corrosion, can be extruded into long continuous sections, has enough flexibility to coil without cracking. The team develops a pipe with a 3-inch steel core for strength, wrapped in lead for corrosion protection, then covered in more steel reinforcement, and finally sheathed in another layer of lead. The result looks like a massive industrial cable about as thick as a man's thigh, weighing approximately 55 pounds per foot. 1 mile of this pipe weighs over 290,000 pounds. Now comes an even stranger problem. How do you transport something that heavy and that long across the English Channel without it sinking your ship? You can't just coil it in a cargo hold like rope. The weight would break the pipe itself. Hartley's solution is genuinely radical. He proposes winding the pipeline onto enormous floating steel drums, each one 40 feet in diameter and weighing 1,600 tons. When fully loaded with pipe, these drums would be towed across the channel by tugboats, slowly unwinding the pipeline to the ocean floor as they go. Think of it like the world's largest and most dangerous fishing reel. But that creates yet another engineering challenge. As the drum rotates and releases pipe, the pipeline naturally wants to spiral and twist as it sinks. Twisted pipe means kinked pipe, and kinked pipe means ruptured pipe. Hartley has to calculate the exact rate of unwinding, the precise weight distribution, and the ideal sinking speed to keep the pipeline descending straight and true. Get any variable wrong and 70 miles of expensive, irreplaceable pipeline becomes 70 miles of useless scrap metal on the channel floor. The metallurgy alone requires innovations that push 1940s material science to its absolute limits. Welders have to join lead sections without creating weak points where the pipe would burst under pressure. Chemical engineers have to ensure the lead alloy won't react with petroleum products and contaminate the fuel. Marine engineers have to account for tidal forces that will lift and lower the pipeline by several feet twice daily. And all of this has to work flawlessly the first time, because there will be no second chance. D-Day is coming, ready or not. Theory is one thing, reality is something else entirely. In early 1943, Hartley's team is ready to test their first prototype pipeline in actual ocean conditions. They choose the Thames estuary for the trial run, close enough to London for easy access, but remote enough to maintain secrecy. Engineers load a shortened section of lead-wrapped pipeline onto a smaller test drum, tow it out into the estuary, and begin unwinding. What happens next is every engineer's worst nightmare. The pipeline sinks beautifully for the first 100 feet, then it starts twisting. The lead sheathing, which looked perfect in the laboratory, begins buckling under the combined stress of its own weight and water pressure. Within minutes, the outer lead layer tears open like wrapping paper. Salt water rushes into the gap between lead and steel core, and the pipeline's internal pressure causes it to balloon outward. Then it ruptures completely, spewing test fluid into the Thames. The entire team watches in horror as months of work literally explodes before their eyes. They haul up what remains of the pipe, and the post-mortem analysis is devastating. The lead layers separated from the steel core during unwinding. Welding joints failed at multiple points. The pipeline twisted far more than calculations predicted, creating stress fractures they hadn't accounted for. Worst of all, even sections that didn't burst show signs of crushing from external water pressure. If they can't make it work in the relatively calm Thames estuary, how will it possibly survive the English Channel during a storm? Hartley goes back to the drawing board, but now he's working against an even tighter deadline. Military planners have tentatively scheduled the invasion for spring 1944, which gives him less than a year to redesign everything. His team tries reinforcing the lead layers with steel wire mesh that makes the pipe too rigid. They experiment with different alloys that flex better, those corrode faster. They adjust the drum unwinding mechanism to reduce twisting. The pipeline still kinks. Every solution creates two new problems. The failures keep coming throughout 1943. One test sees the pipeline sink too fast and slam into the estuary floor, cracking the lead coating in dozens of places. Another test has the pipeline float instead of sink, because air trapped inside the steel core creates unexpected buoyancy. They try adding weight, but that makes it sink too fast again. They try venting the air, but that lets water seep into the core. It's like trying to solve a Rubik's Cube where every correct move on one side scrambles three other sides. By mid-1943, some senior military officials are quietly suggesting they abandon PLUTO entirely and accept the risks of tanker convoys. The project has consumed enormous resources: specialized steel, lead that could have been used for ammunition, engineering talent desperately needed elsewhere. One advisor calculates that PLUTO has cost more than 3 destroyers, and unlike destroyers, the pipeline can't even float properly yet. The pressure on Hartley becomes immense. He's gone from Britain's secret weapon designer to the man who might have wasted millions of pounds and countless man-hours on an impossible fantasy. But Hartley isn't ready to give up. He has one more radical idea, and it requires splitting his approach into 2 completely different pipeline designs running simultaneously. Here's where the story gets really interesting. Hartley realizes he's been thinking about the problem wrong. He's been trying to create one perfect pipeline design, but perfection is the enemy of progress. Instead, he proposes developing 2 entirely different pipeline systems simultaneously. Let them compete, see which one works better, and deploy whichever design proves more reliable. Military planners think this is wasteful, but Hartley argues it's insurance. Better to spend extra resources now than watch the invasion fail for lack of fuel later. The first design keeps the lead alloy approach, but with crucial modifications. Hartley's team redesigns the core structure using a smaller internal diameter of 3 inches and adding multiple reinforcement layers. They call this the WWII pipeline, named after the contracting company Hartley's Anglo-Iranian engineering specification. The lead provides excellent corrosion resistance, and the new layering technique reduces twisting during deployment. Each section weighs slightly less than before, making the massive drums marginally easier to handle. But the WWII's design still requires those enormous floating drums, still needs perfect unwinding precision, and still faces all the problems that plagued earlier tests. The second design takes a completely different approach. Engineers at Siemens Brothers, a cable manufacturing company, propose using steel pipe instead of lead. Now, steel corrodes in salt water, obviously, but they have a solution. Wrap the steel in layers of waterproof fabric impregnated with bitumen, then cover that in steel wire reinforcement, and finally add an outer sheath of more bitumen-soaked fabric. The result looks less like a pipe and more like an industrial fire hose made of metal. They call this the Hemel pipeline, combining Hartley with Hammack, the pipeline directorate's officer Ellis Hammack. The steel design has advantages. It's slightly more flexible than the lead version, which means less stress during unwinding. Steel pipe can be manufactured faster because Britain has more steel production capacity than lead refineries. And if sections fail, steel is easier to repair or replace than lead alloys. But steel also has serious drawbacks. The bitumen coating could crack during deployment, water seeping through even tiny cracks would cause rapid corrosion, and steel pipe is more susceptible to pressure changes, pump fuel too fast, and the pipe could rupture from the inside out. Throughout late 1943, both teams work in parallel, each convinced their design is superior. Arguments erupt during planning meetings. The lead advocates point to superior corrosion resistance and proven underwater cable technology. The steel supporters emphasize manufacturing speed and battlefield repairability. Engineers literally take sides and the rivalry becomes intense. Hartley finds himself mediating disputes, while simultaneously pushing both teams to solve their remaining problems faster. Testing continues in the Thames estuary, now with both pipeline types. The steel Hemel design shows promising early results. It unwinds more smoothly and shows less twisting. But then a test section develops a leak after just 48 hours of pressurized fuel flow. The bitumen coating failed at a weld joint. Meanwhile, the lead HD pipeline survives longer pressure tests but continues having deployment issues. The drums unwind unevenly, creating sections where the pipe hangs suspended in the water instead of resting on the bottom. By December 1943, neither design is fully reliable, and D-Day is now just 6 months away. Hartley needs a miracle, or he needs to pick the least bad option and pray it holds together long enough to fuel the liberation of Europe. D-Day comes and goes on June 6, 1944, and PLUTO isn't there. The pipelines aren't ready. Allied forces storm Normandy beaches while tankers and jerry cans deliver fuel the old-fashioned, dangerous way. Hartley and his team watch the invasion succeed without them, which is both relief and frustration. They've spent 2 years developing this system, and when the big moment arrives, their pipelines are still being tested in British waters. But military planners know the invasion is just the beginning. Keeping Allied armies supplied for the push across France, that's where PLUTO will prove its worth or fail spectacularly. By early August 1944, both pipeline designs have finally passed their qualification tests. The decision is made: deploy both systems and see which performs better under actual combat conditions. On August 12, 1944, the first PLUTO operation begins. Engineers position the massive floating drums called conundrums off the coast of the Isle of Wight. Each drum carries 70 miles of coiled pipeline and weighs more than a small warship. Tugboats move into position, cables go taut, and the slow journey across the channel begins. The unwinding process is agonizingly slow and nerve-wracking. The drums rotate at carefully calculated speed, releasing pipeline that descends through 100 feet of water before settling on the channel floor. Engineers aboard the tugs monitor tension constantly. Too much tension would snap the pipe, too little would cause tangling. Weather has to be near perfect. Even moderate waves could disrupt the process. The first pipeline takes nearly 10 hours to lay completely, and every person involved expects something to go catastrophically wrong at any moment. But it doesn't. The pipe reaches the French coast at Cherbourg, gets connected to pumping stations on both ends, and at 3:47 p.m. on August 12th, fuel begins flowing. The sensation in the control room is electric. Gauges show pressure building, flow rates increasing, and miracle of miracles, no leaks. The pipeline holds. British Petroleum pumps from storage tanks on the Isle of Wight, travels 70 miles underwater through hostile waters, and emerges in liberated France ready to power tanks, trucks, and aircraft. That first day, PLUTO delivers 56,000 gallons, not the million gallons the Allies ultimately need, but it's flowing and it's working. Engineers celebrate briefly, then get back to work because one pipeline isn't nearly enough. Over the following weeks, more pipelines are deployed. Some use the Hayes lead design, others use the Hamel steel design. Engineers lay multiple parallel lines to increase capacity and provide redundancy. If one pipe fails, others keep fuel flowing. By late August, 4 pipelines connect the Isle of Wight to Cherbourg. Flow rates climb to 300,000 gallons daily, then 500,000. The system works so well that planners order expansion to other locations as Allied forces push deeper into France. September brings new challenges. As armies advance toward Belgium, the original Cherbourg pipelines become less useful. Fuel has to be trucked hundreds of miles inland, defeating the purpose of having pipelines at all. So engineers begin a new phase, laying pipelines from Dungeness on the British coast to Ambleteuse and Boulogne in France. These lines are longer and have to cross deeper water, but by now the deployment teams have become experts. They lay pipe faster, with fewer errors, and with growing confidence. By October 1944, the PLUTO network is pumping over 300 tons of fuel per hour across multiple channel crossings. German intelligence still has no idea these pipelines exist. They keep looking for tanker convoys that aren't coming. The expansion phase of PLUTO reveals just how versatile Hartley's radical design has become. Engineers aren't just laying pipelines anymore. They're building an entire submerged fuel network across the English Channel. Each new line requires careful planning to avoid crossing existing pipelines, navigating around shipwrecks, and steering clear of known minefields. The seabed mapping alone is a monumental task carried out by Royal Navy vessels using primitive sonar equipment while trying not to attract German attention. The Dungeness to Boulogne route, completed in late September 1944, becomes the workhorse of the PLUTO system. This crossing is actually shorter than the Isle of Wight to Cherbourg route, only about 45 miles, which means faster deployment and higher pressure efficiency. Engineers lay multiple parallel lines here, creating redundancy that proves crucial when one pipeline develops a leak in early October. Instead of shutting down fuel delivery entirely, they simply close valves on the damaged line and increase flow through the others. Repairs can wait until the damaged section is located and accessed by divers. The system keeps running. By late October 1944, 17 separate pipelines are operational across various channel crossings. 11 use the steel Hamel design, 6 use the lead Ayers design. Interestingly, both designs perform reasonably well under actual combat conditions, though engineers note the steel pipes require more frequent maintenance. The bitumen coating deteriorates faster than expected, especially in sections where strong currents constantly flex the pipe. But steel's advantage is repairability. Damaged sections can be cut out and replaced in days rather than weeks. The fuel volumes flowing through PLUTO by November 1944 are staggering. On peak days, the system delivers over 700,000 gallons. Not quite the million-gallon target, but close enough that tanker convoys can handle the difference with acceptable losses. More importantly, PLUTO provides reliability. Tankers depend on weather, tides, and luck. Pipelines just pump hour after hour, day after day. Allied logistics officers can plan fuel supplies with confidence for the first time since the invasion began. German forces never figure out what's happening. Their intelligence analysts notice that Allied fuel supplies seem impossibly consistent, despite fewer tanker crossings. But they attribute this to better convoy protection or hidden fuel dumps in France. The possibility of underwater pipelines apparently never occurs to German planners, or if it does, they dismiss it as technologically impossible. This intelligence failure costs them dearly. They position submarines to hunt tanker convoys that aren't sailing, wasting fuel and resources on patrols that find nothing. Meanwhile, PLUTO quietly pumps thousands of tons of fuel that power the Allied advance toward Germany. The system isn't perfect. Pipeline breaks occur, usually from anchors dropped by ships unaware of the submerged infrastructure. One pipeline near Boulogne is severed by a drifting mine in December 1944, causing a temporary fuel shortage that delays operations for 3 days. Pumping stations require constant maintenance. The equipment runs 24 hours daily under enormous pressure, and mechanical failures are common. Cold weather in winter 1944 causes viscosity problems. Fuel thickens in the pipes, reducing flow rates until engineers install heating systems at the pumping stations. But these are manageable problems, the kind of operational headaches every major engineering project faces. The fundamental question, can you build a fuel pipeline across the English Channel, has been answered with a resounding yes. Arthur Hartley's impossible design, the project experts called ridiculous, the pipeline that failed a dozen times before succeeding, is now fueling the liberation of Western Europe. When Germany surrenders in May 1945, PLUTO has pumped approximately 172 million gallons of fuel across the English Channel. To put that in perspective, that's enough fuel to drive a modern car around Earth's equator roughly 12,000 times. The pipelines operated for 9 months, under combat conditions, survived winter storms, avoided detection by German intelligence, and delivered fuel more reliably than any tanker convoy could have managed. Military historians later calculate that PLUTO saved hundreds of Allied lives by eliminating the need for thousands of vulnerable tanker crossings. But the story doesn't end with victory in Europe. After the war, most PLUTO pipelines are abandoned in place. Recovering them would cost more than the scrap value. And besides, what would peacetime Britain do with 70-mile fuel pipelines? Some sections are salvaged for parts, others remain on the channel floor to this day, slowly corroding into the sediment. But the technology Hartley developed doesn't disappear. Engineers who worked on PLUTO take their knowledge into the petroleum industry, where offshore oil drilling is just beginning to expand. The techniques for laying flexible pipe across the ocean floor become the foundation for undersea oil pipelines. By the 1960s, oil companies are drilling in the North Sea and need to transport petroleum to shore. They turn to modified versions of PLUTO technology. Flexible steel pipe with protective coatings, wound on enormous drums, deployed by specialized vessels. The modern offshore oil industry owes a direct debt to Arthur Hartley's wartime innovation. Those massive platforms you see in the North Sea, the Gulf of Mexico, and waters around the world, they're all connected to shore by pipelines using engineering principles first proven in 1944 under enemy fire. The technology spreads further. Telecommunications companies adapt PLUTO concepts for laying undersea fiber optic cables. The same problems Hartley faced protecting cables from salt water, managing deployment from ships, ensuring structural integrity under pressure, telecommunications engineers face decades later. Today, virtually all intercontinental internet traffic flows through undersea cables laid using techniques that trace back to PLUTO. Every time you stream a video from another continent, you're using technology descended from a wartime fuel pipeline. Even modern freshwater pipelines crossing large bodies of water use PLUTO-derived methods. Projects like the Baltic Sea Pipeline, various Mediterranean crossings, and proposals for water pipelines across straits all reference PLUTO as proof of concept. If you can pump fuel across the English Channel during a war, you can certainly pump water across peaceful seas in peacetime. Hartley proved that underwater pipelines weren't just possible, they were practical and reliable. Arthur Hartley himself never becomes famous. He receives honours from the British government, quietly accepts recognition from engineering societies, and returns to his petroleum career. He rarely gives interviews and seems uncomfortable with attention. When asked about PLUTO in later years, he typically deflects credit to his team, calling it a collaborative effort under extraordinary circumstances. He passes away in 1963, having witnessed the beginning of the offshore oil boom his work helped create, but probably never imagining that his pipeline technology would one day carry internet data across oceans. The lesson of PLUTO isn't just about engineering, it's about the power of radical thinking during desperate times. When conventional wisdom said underwater fuel pipelines were impossible, Hartley asked, "What if they're not?" When early tests failed spectacularly, he didn't quit. He redesigned and tried again. When one approach didn't work, he developed two competing systems simultaneously. This kind of determined innovation, backed by meticulous engineering and willingness to fail forward, changed the course of history. D-Day gets the glory, and rightfully so, but PLUTO provided the fuel that turned invasion into liberation, and turned one engineer's radical design into the foundation of technologies we still use 80 years later.